Hello friends of the Isothermal channel. Flash calculations are at the heart of chemical process simulations. There are many problems of interest such as isothermal flash calculations, adiabatic flash calculations, among several others. And even for a given type of calculation, such as an isothermal flash, there are many different algorithms available in the literature. In this video, we are going to solve an isothermal flash problem using a very fundamental idea in thermodynamics, namely that the equilibrium state of a system whose temperature, pressure, and component amounts are specified coincides with the state of minimum Gibbs energy. Our example deals with a mixture of carbon dioxide and clove oil. Clove oil is of vegetable origin and is a complex mixture of many compounds. For simplicity, we'll lump all of them as a single pseudo-compound. Specifically, we are going to deal with a mixture that contains 93% on a molar basis of carbon dioxide at a temperature of 318.2 Kelvin and at a pressure of 100 bar. Such high pressures are typical of supercritical fluid extraction processes. And at such high pressures, the use of equations of state to calculate phase equilibrium is particularly attractive because calculations with activity coefficient models may be inaccurate at such conditions. We'll use the Peng-Robinson equation of state with quadratic mixing rules for the A and B parameters. The conceptual situation behind the flash problem we want to solve is having a feed stream of known flow rate and composition entering a flash drum where it splits into a liquid phase and a vapor phase. It's important to note that we do not know beforehand the composition and the amount of the liquid and vapor phases. However, we do know that the mass balance for each component should be satisfied, and therefore the flow rate of each component in the liquid phase plus the flow rate in the vapor phase should be equal to the flow rate of the feed stream. The Gibbs energy of this system is given by the summation of the Gibbs energy of the liquid and vapor phases. Here, all of them are divided by RT, and remember that the temperature is constant in this problem because it's an isothermal flash tank. And the Gibbs energy of a phase is given by the summation of the product of the component amount by its partial molar Gibbs energy. And the partial molar Gibbs energy is the chemical potential of that compound. And this chemical potential divided by RT is equal to the summation of the chemical potential in the ideal gas state divided by RT plus the logarithm of the ratio of the fugacity coefficient to the pressure of a reference state. The fugacity is equal to the product of the mole fraction by the fugacity coefficient by the system pressure. In the last expression of this slide, the term between brackets contains composition-independent terms. The composition-dependent terms, ln of xi and ln of phi I, are left outside the brackets. Here we have developed this expression for the liquid phase, but an entirely analogous development can be made for the vapor phase. We can now put the contributions of the liquid and vapor phases into a single expression for the Gibbs energy divided by RT. This is an intermediate algebraic step in the development. When written as shown in this slide, the first term on the right-hand side of G over RT is a constant in an isothermal flash problem because it depends on temperature, on pressure, and component amounts, all of which are known beforehand. By moving this term to the left-hand side, we can now define a delta G over RT as given by equation 9. From a practical standpoint, our mathematical problem will be to minimize delta G over RT. The problem unknowns are, in principle, the amount of each component in each phase. Instead of using them directly, it's convenient to use the so-called distribution factors, defined as the amount of a given component in a phase by the total amount of that component in the system. In this way, These distribution factors are always numbers between 0 and 1, and Excel Solver tends to work better when all variables, all unknowns, are of similar scale. In addition, when added over all phases for a given component, the result is equal to 1 because of mass conservation. Here is our spreadsheet, and the color convention is that the cells with orange background are specifications and all others are the results. We are going to use the Peng-Robinson equation of state with quadratic mixing rules for A and B, and the mixing rule for B has Lij as binary interaction parameter. This is the reference to the Journal of Chemical Engineering data paper that motivated this example. And we have as specifications the value of the universal gas constant, the temperature and pressure of operation, the properties for CO2 and clove oil, the pure component properties, critical properties and eccentric factor, the Kij for A, the Lij for B. Here, the cells with blue backgrounds are initial estimates for theta. These are the total amounts of CO2 and clove oil in the system, and the total amount in the system altogether is equal to 100. The amount in the liquid phase of CO2 is theta of CO2 times the number of moles of CO2 in the vapor phase, theta of CO2 in the vapor times the total amount, and we can drag laterally to get the amounts of clove oil in the same phases and the total amounts in the liquid and in the vapor. We need them because we need to calculate the mole fractions in the two phases. So this is what we are doing now, dividing the amount by the total amount. So we are going to do this for carbon dioxide. We are going to in the liquid phase. Now we are doing for the vapor phase. And we are going to get the mole fractions of clove oil in the liquid phase and in the vapor phase. Next, we are going to calculate the logarithm of the fugassity coefficients. And to do that, we are going to use a function called PRB2 len phi L to indicate we are going for the properties of the liquid phase. The first argument this function takes is the value of the universal gas constant, which we lock with F4. Next, the temperature, also locked with F4. The pressure, locked with F4. The mole fractions. And the parameters that characterize the mixture, also locked with F4. We close the parentheses, and now we press Ctrl, Shift, Enter to get the logarithm of fugassity coefficients. We drag down, and now we do some little editing to change len phi L by phi V to get the properties of the liquid phase, and again Ctrl, Shift, Enter. Now we add the logarithm of the mole fraction to the logarithm of the fugassity coefficient, and we do this for all components in all phases. We can now calculate delta G over RT for the liquid phase. To do this, we'll consider first the product of the amount of CO2 in the liquid phase times the summation of the mole fraction, len of mole fraction, len phi, and we do the same for the contribution of clove oil. By dragging down, we get the corresponding value for the vapor phase, and adding these two contributions, we get delta G over RT for the system, which we now need to minimize, and we call solver. Our set objective is to minimize this cell, minimum, and we will change the theta values that have blue background. We press solve, Excel works on it and has the answer now, which appears here. This is the summary of our solution. The amount in the liquid phase is equal to 24.22 moles, and in the vapor phase it is equal to 75.78 moles. The mole fractions in the two phases appear on this slide, and we observe that the mole fraction of clove oil, substance 2, is way higher in the liquid phase than it is in the vapor phase. This concludes our presentation, in which we solved an isothermal flash problem, that is, a flash problem with specifications of temperature, pressure, and component amounts using Gibbs energy minimization. Thank you very much for watching this video. My name is Marcelo Castier, and let me take this opportunity to invite you to subscribe to our Isothermal channel and to visit the channel's page on Facebook. Thanks again, greetings, and bye for now.